This is VLSI data conversion circuits, lecture 28. In the last class, we were looking at a way of implementing the loop filter in continuous time right. So, this was a system we were examining towards the end of the last class, where the basic idea is to make a continuous time filter mimic the behavior of a discrete time loop filter. Okay. And as we saw the last time around, what we want to do is to make sure that the cascade of the DAC pulse shape P of t along with 1 over s behave equivalently to Z inverse by 1 minus Z inverse, right. This way the loop gain of the loop, if you break the loop here for example and you inject an impulse and see what sequence comes back, then if the loop filter is chosen to be 1 by s for the first order case, the whole system will be indistinguishable from having a discrete time loop filter whose transfer function is Z inverse by 1 minus Z inverse. Is this clear? So, as far as the noise transfer function is concerned, the last time around we looked at a pulse shape P of t being the NRZ pulse, right, and I would like to remind you again that sampling rate is normalized to 1 hertz. You can always take this the values of the components or whatever you get in a 1 hertz normalized schematic and scale them so that it gives you the same noise transfer function at some other sampling rate. The advantage of scaling everything to 1 hertz is that the numbers all become all component values will have the same order of magnitude, okay, and you do not have to worry about Fs and things like that in the formulae, which will prevent you from making errors. This is a standard thing to do in all filter work, right. You always assume that your normalizing cutoff is 1 hertz or 1 radian per second as the case may be, work everything out and then scale this prototype to whatever other frequency that you want, alright. Okay. So, the basic idea as you can see is to make sure that the samples of the loop filter driven by the DAC pulse must be exactly equal to the impulse response of the loop filter from the port V to Y. You understand? In other words, to the left of this green line, okay, what one would traditionally find would be a discrete time loop filter, and all that is happening now is that this continuous time system, please note that P of t, the pulse shape of the DAC, is instrumental in transforming the input sequence V into a continuous time output waveform V of t. Is that clear? This is a discrete time sequence. V of t on the other hand is a continuous time waveform. To transform V of n into V of t, one needs to have a pulse shape which is being provided by the DAC. As I discussed the last time around, there are several possible pulse shapes. A common thing to use is what is called the non-return to 0 pulse shape, which stays put at 1 all the way from 0 to 1. You can also have the so called return to 0 pulse, which is height 2 and a width of half, and similarly an exponentially decaying pulse and many other pulses also, but for simplicity we will consider the non return to 0 pulse in the beginning. So, P of t convolved with the impulse response of the loop filter, the continuous time loop filter, must mimic after sampling the impulse response of the discrete time loop filter, right. So, in general, therefore, if I assumed a CTDSM of this nature, then what it means is that P of t exciting this loop filter and sampled should be exactly identical to L of z where L of z is the discrete time loop filter that one wanted to realize, and L of z is obtained from the noise transfer function from as once you know the noise transfer function, you can determine L of z using the relation NTF of z is 1 by 1 plus L of z. Is this clear? Okay. Now, this is what is called the principle of impulse invariance. You must have seen this in your DSP classes, right. So, the job at hand is to figure out, given L of z and P of t, what is L of s which enables these two sequences to be identical when excited by an impulse, a discrete time impulse, mind you, at the input. Is this clear? For the first order case, we found it was quite straightforward to do, all right. We will now go forward and see what one can do, how one can compute this in the more general case, where the NTF of Z is not simply 1 minus Z inverse, but something of the form 1 minus Z inverse to the n divided by some d of Z inverse, which is what which is the usual kind of noise transfer function one deals with. Okay. But before that, let me also point out an interesting property, and I will illustrate that using the first order continuous time delta sigma modulator. I have replaced the ADC DSC combination with an additive noise source, and this is U, and this is V of n, this is V of t, Y of n. All right. When we were analyzing the response of this modulator to continuous time inputs, the last time around we said that if the input is slowly varying, which is definitely the case, because by construction this whole thing is supposed to be an oversampling system. So, the rate at which the input varies from clock cycle to clock cycle is very small, right, in which case one can replace the continuous time system, the continuous time input signal, with a stepped approximation right, in which case you can think of the input as being sampled, convolved with a impulse response p of t before getting into the continuous time loop filter, right, and then we isolated the 1 over s along with the pulse shapes, and then determined that it is equivalent to a discrete time loop filter which was Z inverse by 1 minus Z inverse. So, for all practical purposes this is exactly equivalent to the noise transfer function is the same as a first order discrete time modulator. The signal transfer function is also the same as a within the signal band, at least the signal transfer function is also the same as a first order delta sigma modulator. So, it seems as if there is no difference between the two. However, as far as the signals are concerned, the stepped approximation is only valid when the input signal is very slowly, right. One thing that we find interesting is that what happens to this loop when the input is not at DC, but at the sinusoid at Fs, right, in this case at 1 hertz. In a regular A to D converter, for example, either in a Nyquist rate converter or in a discrete time delta sigma modulator, if the input was at the sampling rate, what would happen to the output sequence? Any sinusoid at multiples of the sampling rate will alias to DC. So, taking this a little further, frequencies around the sampling rate will alias to frequencies within the signal band, all right. So, let us here there is a difference in the way the A to D converter is built, because the sampling is not happening up front, but is happening inside the loop, that is at the output of the loop filter, right. So, we would be interested in figuring out what happens to the what happens to how does the loop respond to an input at high frequencies or at an input which is at multiples of the sampling rate. Okay. To see what the loop does, let me manipulate the loop a little bit. For starters, what I am going to do is to move this 1 by s through the summer. So, what I will get will be this is V of t now. Is this clear? Is the transformation from here is this clear? All that I have done is move the integrator or the loop filter in general through the summer. This is mathematically equivalent. Okay. Do you think this is a practical way of implementing the loop? All of you agree that this is mathematically equivalent, correct? So, do you think this is a practical way of, can I implement this loop? This is an aside and not directly relevant to our discussion, but I am just out of curiosity I am asking you, do you think it is practical to implement the loop like this? Why? The integrator is outside the loop, and we all know that an integrator working open loop will saturate. Okay. But as far as analysis is concerned, we are perfectly free to do this, okay, because mathematically it is equivalent. All right. Now that I have moved the integrator outside the loop, I would also like to move the sampler through the summing node, so to speak. So, the next point in the evolution is to copy and paste and move this way. All right. Is this clear now, everyone? So, I mean, you might wonder why one would do this kind of manipulation, right? The reason for this is the following: to analyze this loop is kind of difficult. Why? The problem with this is that it consists of both continuous and discrete time systems, and there is a feedback loop to boot. So, it is not, I mean, it is not impossible to do, but it seems somewhat messy to do. So, one way of kind of approaching the problem is to try and split this up, where the continuous time part is separate and the discrete time part is separate. Then we can analyze the discrete part using Z domain techniques and the continuous time part by S domain techniques, and somehow stitch the two and figure things out. Since mathematically the whole thing is equivalent, right, the final answer we get must be correct. So, as a first step we push the continuous time part out, alright. Then we moved the sample and hold also in such a manner that this part is now completely can be interpreted as a discrete time system. Why? Because this by definition or by choice of the integrator, this is nothing but L of z. You understand? And once we replace the cascade of P of t 1 over S and the sample and hold by L of z, this system here is completely, so on this side it is continuous time, or rather to the left of the sampler it is continuous time, to the right of the sampler it is discrete time. You understand? Okay. Now, what is it, the given this sequence, what is the transfer function from E to the output? What is the transfer function from this sequence to the output? It is not surprisingly that transfer function is E of z times 1 by 1 plus L of z, and the way we have chosen L of z is that this is nothing but the NTF that we want times E of z, correct. What we are interested in is the response from U to the output sequence V, alright. So, how do we attack this? What is the response from here to V? It is the same as the NTF, because you know you can think of this quantization error as the input to this loop, correct. This is clear. So, if I call this intermediate signal say x of n, then the transfer function from x to V is nothing but 1 by 1 plus L of z is V of z, correct. But what is the transfer function from U to x? Alright. If I told you that U was a sinusoid at a frequency f and had an amplitude A, so A cos 2 pi f I times t, how will you figure out what V is? Yes.
This from 0 to t.
Okay.
Then replace.
No, not 0 to t. This is a continuous time integrator. It is not minus infinity to t. That is correct.
And then replace t with n into ts.
Correct. Yes. So you will get a you will get a discrete time sinusoid. Correct. And once you know that, you know the discrete time transfer function from x of n to v. So you can just write you can just plug in the appropriate value for z, which will be e to the j blah blah blah, and determine the magnitude of the sinusoid at v given u, right. So in other words, this signal here is of the form a by 2 pi f I, right, sin 2 pi f I into t So, after sampling, what will this result in? A by 2 pi f I times sin 2 pi f I times n, because I assume that T s is 1. Let me put that down here. The sampling rate is 1 hertz. All right. So, as far as x of n is concerned, it is a discrete time sinusoid with some amplitude, which happens to be in this case a by 2 pi f I. Is this clear? Now, this goes through 1 by 1 plus L of z, which is in this particular example a noise transfer function, which is 1 minus z inverse. So, to determine, please note that our aim is to determine the amplitude of the sinusoid at V, which is the output of the modulator, given the amplitude of a continuous time input sinusoid at u, right. And because we have split our system up as a continuous time system cascaded by a discrete time system, we propagate the sinusoid through the continuous time system, and the output of the continuous time system, that is here, will simply be a tone at the same frequency, but whose amplitude and phase will be changed depending on the transfer function of the loop filter, right. That is sampled, and where is aliasing occurring? The sampling action is what is responsible for the aliasing action, correct. So, if f I was f s plus delta f, for example, then after sampling it will look like a sinusoid at delta f, you understand, okay. So, this sinusoid here, because of aliasing due to sampling, will always be such that its frequency lies between 0 and pi, okay. Now, we know the transfer function from x to the output, which we said is the same as the noise transfer function. So, given the amplitude of the sinusoid at x of n, it is very straightforward to find the amplitude of the sinusoid at V, because we know the transfer function, correct. So, if I plot L of s as a function of or the magnitude of the continuous time loop filter's gain as a function of input frequency, how will it look like? At DC it will be no, linearly. No, what is the gain from u to the output of the loop filter as frequency is changing? It decreases. At DC it is infinite, and it falls off as 1 by Fi, right, 1 by 2 pi Fi is the correct expression, correct. But at low frequency, what I want to point out is that it goes as 1 over Fi, alright. Now, if Fi exceeds 1 hertz, I have just chosen some random x axis, right. So, let us assume that we are now interested in determining the response of this loop to frequencies which are at multiples of the input sampling rate. If the input is at 1 hertz plus delta f, you can see that the amplitude of the input is, after the loop filter, is something like that. That is the amplitude of the discrete time alias tone after sampling, okay, and that has to be multiplied by NTF. And so, to show it on the same picture, the sampling rate corresponds to how many radians in the discrete time domain? 2 pi. So, this is 4 pi, 6 pi and so on. At pi, what is the gain of the NTF? 1 minus Z inverse, it is 2. At 2 pi, what is the gain? All right, and this will be periodic, like, I am sorry, it must be exactly the same. All right, does it make sense? So, an input tone at DC, let us understand what happens. We know the answer. If the input is DC, what should the output be? In this modulator, if the input is DC, what would one expect V of n to be? It must be the same DC, correct? All right. Now, we should expect to get the same answer, because this block diagram is nothing but a manipulation of the original one. So, let us make sure that we get we should expect a DC gain of 1 even after we analyze this. So, at DC, this goes as, okay, or if you consider a small frequency delta f, this goes as 1 by delta f, all right. And what about what happens to this guy? this goes as delta f. Okay. So, when you multiply the 2 you get 1, you understand. You might wonder what happens to the 2 pi, since we are always dealing with frequencies rather than radians per second. Okay. The 2 pi is also cancelled out, otherwise the gain of 1 over s is proportional to 1 by omega, the NTF at low frequencies is proportional to omega, and the 2 cancel out and you get a DC gain of 1. Alright. Now, let us see, so at DC the magnitude of the STF is 1. Now, at a frequency delta f, or rather at a frequency 1 plus delta f, what do you think will be the gain, no, pardon, no,
No, delta f by what, delta f by 1 plus delta f.
delta f divided by
1 plus delta f.
Okay, delta f divided by 1 plus delta f, and how do you get that? Okay, very good. Okay. So, you can see that at a frequency input which is 1 plus delta f, where delta f is a small number, right, what will happen? A cos of 2 pi to 1 plus delta f times t. At the output of the integrator, what is the amplitude?
Divided by 1 plus delta f.
A by
1
plus, I mean A divided by 2 pi times 1 plus delta f, but after sampling what is the frequency? Yeah. So, even though these two tones, so let me write that down here. So, we had the loop filter which is 1 by s, we consider two cases, A cos 2 pi delta f times t and A cos 2 pi into 1 plus delta f times t, right. After sampling, what happens to the first tone? The amplitude is A by 2 pi delta f sin 2 pi delta f times n. Okay. What happens to the second tone? A by 2 pi into 1 plus delta f sin 2 pi into 1 plus delta f times n, which is exactly the same as 2 pi delta f times n. Okay. So, both these tones alias to the same discrete time frequency. This is well known, right, because sampling is involved, you will have multiple tones aliasing to the same discrete time sequence. However, you see that there is a big difference in the amplitudes, right. So, the discrete time system following this is the same in both cases, right. So, both these tones alias to the same frequency in the discrete time domain, after which the gain in the discrete time domain is the same for both. So, what is the gain of an input? So, the ratio of the STF at delta f to the STF at 1 plus delta f must be in this case what?
1 by 1 plus delta
It is simply 1 plus delta f by delta f. You understand? Okay. And note specifically that if the input is exactly at the sampling rate, what happens to the output? STF at 1 plus delta f is nothing but STF at delta f multiplied by, in this particular case, delta f divided by 1 plus delta f. If delta f is 0, in other words, if we put in a tone at the sampling clock frequency, which in a normal converter would cause severe aliasing, because the same tone will appear, a tone at the sampling rate will appear like DC. Okay. So, it will simply alias unless you put a very strong anti-alias filter which removes tones at beyond Fs by 2. You understand? We saw this in the very beginning of this course, that if you have to have a sample and hold, to prevent aliasing you must have a very sharp filter which eliminates tones which can alias into your signal band. Okay. So, at delta f equal to 0, we see that, or for delta f equal to 0, the magnitude of the signal transfer function at 1, which is the sampling rate, okay, is STF at 0 times 0. STF of 0 is what? The STF at DC is 1. So, we see that we now have the remarkable property that at multiples of the sampling rate, in this first order example, there are nulls in the STF, which is great news, because what does this mean? This means that in principle we do not need an anti-alias filter, because at multiples of the sampling rate the signal transfer function goes to 0, right. So, it is as if you have something which eliminates all tones at Fs. Similarly, at frequencies which are close to the sampling rate, that is small delta f, the alias rejection is, or the response to tones at 1 plus delta f is this delta f divided by 1 plus delta f, which is approximately delta f itself, right. And delta f by design will be a small number, because this is an oversampling system. The input frequencies that we are interested in are such that this delta f will be of the order of pi by OSR, right, or will be very small compared to 1. So, for frequencies in the neighborhood of Fs, you will get an STF which is close to 0. At Fs, of course, the signal transfer function is actually 0, but at frequencies close to Fs, you will get a signal transfer function which is of the order of delta f. Okay. So, the delta f will be of the order of 1 by OSR. Okay. So, if it is actually it will be 1 by 2 OSR, because F in by Fs by 2 is the OSR, is 1 by OSR, sorry. Okay. So, this the delta F numbers that we are talking about in practice will be of the order of 1 by 2 OSR. So, with a first order delta sigma modulator, I mean, is this clear why this is 1 by 2 OSR? No. Okay. So, F in by Fs by 2 is 1 by OSR, which means that the input frequency divided by the sampling rate is 1 by 2 OSR, correct. So, if we are talking about signals aliasing into the desired band, it must follow that this delta F must be smaller than 1 by 2 OSR. Does it make sense? Right, which means that for frequencies which are around the sampling rate, please note that I am grossly exaggerating here, right. If this is the desired signal band and this is Fs and this is 2 Fs and this is 3 Fs and so on, where are the alias bands? Fs plus minus Fb, alright. The STF at DC is, what is the STF at DC? 1, and at low frequencies you can expect it to be close to 1, correct. So, at DC or in the signal band the STF is close to 1. At Fs, what is the STF? At multiples of Fs it is 0, at frequencies close to Fs it is close to 0, right. It turns out that all right. And how will this fall off? It must fall off as 1 by f. And why is it 1 by f? Because the signal transfer function is nothing but the magnitude response of the integrator, which falls off as 1 by f multiplied by this periodic noise transfer function, correct. At DC the noise transfer function is going as omega, the loop filter is going as 1 by omega. So, the two of them cancel and you get 1. At high frequencies the noise transfer function at frequencies which are 1 plus delta f or at Fs plus some small frequency, the noise transfer function is still going as omega, right, but the response of the integrator is reduced significantly, which means that the gain must fall. And what I am saying is that in the special case of the first order system we have been discussing, this alias rejection, which is the maximum gain in this band, right, will be at least 1 by, the attenuation of these signals will be at least 1 by OSR times 2. Is this clear? What about the attenuation here in the second alias band? It will be at least delta f by 2 plus delta f is very small compared to 2. So, it is roughly 1 by 4 OSR. And 1 by 6 OSR and so on. Okay. All right. So, intuitively this makes sense because the loop filter treats a sinusoid at 1 plus delta f very differently from a sinusoid at delta f, okay, and the loop filter output is being sampled. This is in contrast with the discrete time delta sigma modulator, where sampling is happening right up front. So, the treatment given to a sinusoid at 1 plus delta f is exactly the same as the treatment given to a sinusoid at delta f. So, in other words, a discrete time modulator, as we expect, cannot distinguish between a sinusoid at 1 plus delta f and a sinusoid at delta f. It will have the same magnitude for the STF for both these sinusoids, okay, which is why you need an alias anti-alias filter up front, which will attenuate components in the alias bands to a sufficiently large degree, so that you do not incur alias errors. Whereas, in a continuous time modulator, by virtue of continuous time operation of the loop filter, we see that at multiples of Fs, the STF is indeed 0, okay, and for frequencies which are close to Fs, the STF is small, okay, thereby it appears as if you have cascaded a anti-aliasing filter up front, which greatly reduces the gain for the input signals in the alias bands. Okay. So, this property is called the implicit anti-alias property of a continuous time delta sigma modulator. Right. So, in the next class we will generalize this to high order loop filters and see what the signal transfer function is in that case.